Hey everyone, this is lecture 12. This is the first lecture after reading week, and this is the beginning of the second half of the course. And this week we're going to introduce statistical inference. I want to begin this lecture with a little game of heads or tails with coin flipping. And normally we would do this game in person in the classroom, but instead I'm going to play you a short video clip of me demonstrating this game with my daughter. As you watch this clip and see what unfolds, I want you to be a skeptic, and I want you to think, do you trust what's going on, or do you have some doubts? And if your feelings change as this movie clip plays, at what point do your feelings change? Okay, here we go. Okay, we're going to have you guess 10 times in a row what this coin lands on, heads or moose. Let's see how many you can get right. Are you ready?
Yes.
Here comes the first one. What's your guess?
Moose.
You're right. Heads or moose?
Heads.
You're right. Here, come a bit closer. You got two. Heads or moose?
Moose.
You're right. Three. Heads or moose?
Heads.
You're right. Four. Heads or moose?
Heads.
You're right. 5 in a row. Do you think you can get all 10?
Moose.
You're right. 6. Do you think you're going to get all 10 of them right?
Yes.
Wow. Okay, what's your next guess?
Moose.
You're right. 7. Okay. What's your guess for this one?
Heads.
You're right. 2 more. What's your guess for this one?
Heads.
You're right. Wow. What's your guess for this one?
Moose.
You got all 10. Are you surprised?
Yeah.
Okay. All right, so was I telling the truth? Did you think I was being honest, or did you begin to have doubts or suspicions about what I was telling my daughter during that game? And if you developed doubts, at what point, which coin flip in that series of 10 coin flips did you become suspicious? So we're going to introduce statistical inference today and cover this for the second half of the course. And this topic is going to draw on a lot of the fundamental skills that you learned in the first half of the course. Today we're going to focus on introducing the procedure of null hypothesis statistical testing. So we'll talk about what it is, what the steps are to null hypothesis testing, why we use it, and you'll be expected to know some of the other things listed on this slide. So remember from lecture 5, statistics is a method for describing and measuring aspects of nature from samples. We need statistics whenever the features of things we're trying to study are variable or noisy or unpredictable from one sample to the next. In this lecture, we're going to introduce inferential statistics. This is the process of hypothesis testing or determining how well our observed data fits with a particular hypothesis and null hypothesis. Okay, so we'll start with a little example here. This is a real example about the disease polio, which is a huge problem in the early 1900s, up to mid-1900s. It was a common disease and it had really detrimental effects on young children. Many children died, many children were permanently paralyzed from polio infections. And there was an outbreak in 1952 where nearly 60,000 children contracted polio in the United States. And more than 3,000 of those children died, and many more were lifelong effects. It was a problem in Canada as well. So here we see 2 bar graphs. On the top, we're seeing a graph across different years of the number of reported cases of polio, both in the province of Manitoba, shown in beige, and then the orange bars are the case counts for all of Canada. And you can see how it became increasingly these infections were becoming increasingly common as we got into the 1950s. And in the lower graph, we're seeing an estimate of polio deaths per 100,000 people, both in Manitoba and all of Canada. And this is showing that Manitoba was hit particularly hard. So it was really important to find a vaccine, a way to avoid all these terrible effects of polio. So in 1954, an experiment was conducted on a new vaccine developed by Jonas Salk. And the subjects in the experiment were a little more than 400,000 children in the US and Canada, huge sample size. And the subjects were randomly divided into two groups. The treatment group, those children received the polio vaccine that was newly developed, and the control group got an injection of sugar water or a placebo. And the question was this new vaccine effective? This was such an important question at the time because the US and Canada needed to know, should we spend millions of dollars producing this new vaccine and distributing it to everyone in North America? Is it going to solve these terrible effects? Okay, so here are the data. So half of the people were given the vaccine, half the placebo. And they followed up with those children sometime later and determined whether or not they had contracted polio. And so what you're seeing here is a contingency table showing the data from this experiment. So we've got two columns. We've got the vaccine group and the placebo group. And then we've got the two rows. Did the people who got polio and people who did not contract polio. So we've got a table here showing you counts of people for these two categorical variables, right? We've got our treatment variable as our columns, and we've got our health outcome as our two rows. And so, okay, so just looking at this column or this table right away, you can see, all right, more of the children in the placebo group got polio than in the vaccine group. However, is this difference the kind of difference we might get just by chance? Remember, every time you draw a sample, you're going to have differences in the sample proportion or other descriptive statistics. So is this the kind of difference we might see just by chance, or is this likely to be a real effect of this vaccine? So what we need is some estimate of certainty around these numbers. Okay, so we can use the data in this table to calculate some proportions and percentages. And so if you do that, you can say that 0.016% of children in the treatment group got polio and 0.057% of children in the placebo group, the control group, got polio. Okay, so the question is this vaccine effective? Okay, so here's just an overview. This diagram shows the whole point of what we're doing here. So we want to know about some parameter of the population. And in this case, the parameter would be whether the vaccine is more effective than the placebo. So that's a feature of our population. But what we have to work with is a sample. So we draw a sample and we take a measurement from the people in our sample. In this case, we measure whether they got polio. And so we get some estimates from that sample. So we get estimated rates of polio contraction in our two groups in our sample. And so we want to take those estimates and draw an inference about the population parameter and draw some conclusion about our original question as to whether this vaccine was more effective than a placebo. So inference is the process of calculating certainty on our estimates so that we can test hypotheses or make conclusions. Okay, so hypothesis testing is when we compare a data set to an expectation derived from a null hypothesis. Now we're going to get into examples of null hypotheses as we develop this lecture. And so the whole idea here is that if the data we got are too improbable, too unlikely, too surprising under the assumption that the null hypothesis is true, then we reject the null hypothesis. Now, I just want to pause and say this is a really convoluted, hard to wrap your head around thing. So be patient with yourself as you're learning this. We're going to hit on it again and again in this latter half of the course. And so give yourself lots of chances to practice this because it's really counterintuitive. All right, so what is the null hypothesis? Well, the null hypothesis is a statement about a population parameter that negates our research hypothesis. And a good null hypothesis is something that we would like to reject. And so for this polio vaccine experiment, our null hypothesis might be that the new polio vaccine is no more effective than sugar water. Okay, so we'll come back to that example in a few slides. I want to look at the coin flipping example, and I want to use it to kind of illustrate the process of null hypothesis testing. Okay, so you saw my daughter guess a flipped coin, and she had to do it 10 times in a row. And I reported as she was guessing that she was correct 10 times in a row. Amazing. That's like incredible guesswork. But do you believe it? Did you believe that I was telling the truth, or did you think I was trying to boost my daughter's confidence or something like that? Okay, so let's use this example to walk you through the steps of null hypothesis testing. All right, so the first step is to formulate the question and the null hypothesis. So the question is whether I'm being honest or not. And the null hypothesis is that I am being honest, and the probability of guessing correctly on any one coin flip is 50% or 0.5. Our main hypothesis is that the probability of guessing correctly is different than 0.5 because I'm not being honest. Okay, so the next step in null hypothesis testing is to calculate descriptive statistics and determine the value of the test statistic for the observed data. The test statistic is a measurement calculated from the observed data that's used to evaluate how compatible the data are with a null expectation. And what the test statistic is will depend on the question, it depends on the analysis. In our coin example, let's assume that the test statistic is the number of correct guesses and the value we observed was 10. Okay, so step 3 is to determine the null distribution of the test statistic. So the null distribution is a probability distribution. It tells us here are all the possible outcomes, and here is the probability of all of those outcomes occurring if we assume the null hypothesis is true. So we can do that for this coin flipping example. It's kind of this beautiful example because you can calculate that null distribution pretty easily. And I've done that below in this graph. So here's what it looks like. So this is a probability distribution. It's a lot like a histogram, but it's a bunch of probabilities. And so on the x-axis, we have all the possible outcomes of our little experiment, right? So my daughter could have had 0 guesses correct, 1 guess correct, 2 guesses correct, 3, 4, all the way up to 10 guesses correct. And what I've done is I've calculated the probabilities. If the null is true, if the probability of guessing correctly is really 0.5, these are the probabilities that somebody would get that each of those correct guess numbers. We'd get each of those test statistic outcomes. The highest point on this probability distribution is for 5 correct guesses. So that's the most likely outcome. But it's pretty likely for someone to get 4 correct guesses or 6 correct guesses, somewhat less likely to get 3 correct guesses or 7. And as you get into the extremes, as you get into 10 correct guesses or 0 correct guesses, those outcomes are really unlikely if we assume the null is true. So I've drawn in blue here what actually happened. In that video clip, there were 10 correct guesses in a row. That's our observed outcome. That's our observed test statistic. And here's the most likely outcome, 5 correct guesses. And what we do with null hypothesis testing is we use this null distribution and we calculate the probability of getting data at least as extreme as what we observed if the null was true. And this probability is p, or the p-value. All right, so we need to calculate the probabilities of anything equally or more extreme than what we observed. And so that would be 10 guesses, and equally extreme would be getting 0 correct guesses. So what we do is we determine the probability of 10 and the probability of 2, and we add those together. And so that summed gives us the probability of getting an outcome at least as extreme as the one we observed. And in this case, that sums up to a probability of 0.0019. So therefore, our p-value is 0.0019. So that's if we assume that the coin is fair and that I'm not lying, that's the probability of getting the outcome that we observed. Okay, so just to say that one more time, the p-value is the probability of getting a result at least as extreme or more extreme than what we actually did, assuming the null hypothesis is true. Okay, so now that we calculated the p-value, what do we do with it? Well, if the p-value is small enough, we reject the null hypothesis. Otherwise, we do not reject it. But this raises a question. What do I mean by small enough? Like, what is small enough to reject the null hypothesis? Just to put into kind of plain language what we're doing here, a small p-value is telling us that it was really surprising, really improbable to observe a result like this under the assumption that the null is true. Okay, how small is small enough? How unlikely does the outcome have to be for us to be satisfied that we can reject the null hypothesis? Well, in biology, by convention, the boundary for small enough is a p-value less than 0.05 or 5%. Now, this is an arbitrary choice. It didn't have to be this way. That's what people most commonly use in biology, but there's nothing magic about 0.05. And so we refer to the threshold that we use for p-values for determining whether to reject the null hypothesis. That threshold is called the alpha level, or alpha. Okay, so to apply that threshold, we can say if p is less than 0.05, we reject the null, and otherwise we do not reject it. And I just want to point out, again, it doesn't have to have been 0.05, that's the most common one, but some fields of research use a more stringent alpha level. Like, for example, some use an alpha of 0.01, especially in medicine, and so that would mean that you would not reject the null unless your p-value was smaller than 0.01. Some biologists have argued that all researchers should be using a more stringent alpha of 0.005 or even 0.001. And in other fields, there are different thresholds of probability. For example, physicists doing research on high energy particles using these big particle accelerators, they use a 5 sigma alpha level, which refers to a threshold of 0.0000035. So an event in these particle accelerators has to be really improbable for them to get excited. Okay, so coming back to our coin flipper example, we want to compare our calculated p-value to our alpha threshold, and then we want to report the results. And in addition to your conclusion about the null hypothesis, there's other elements that you should report as well. For example, you should report your descriptive statistics and or your test statistic, and that shows the magnitude of the effect. You should report the type of statistical test that you used, the sample size, and by now you should know why that matters. And you should report the p-value, which shows how you drew the conclusion you did. And if you're missing any of these 4 parts, it makes it difficult for the reader to tell how you came to your conclusion. Okay, so here's an example of how we could report on results of our coin flipping game. We could say, we observed a success rate of 100% correct guesses, or 10 correct guesses in a row, leading us to reject the null hypothesis that Dr. Dakin was being honest. The p-value here is 0.0019. The sample size was 10 coin flips. So we've got our descriptive statistic, which shows us the magnitude of the effect. We've got our p-value, we've got our sample size, and we've got our conclusion or our interpretation reported here. I did not report the type of test, mostly because we haven't learned what type of test this is yet. It could be reported in the sentence. For example, it could be reported in the parentheses with the p-value and the sample size. If this was a scientific paper, it could also be reported in the methods section. Okay, here's another example of reporting, this one involving the polio experiment. The incidence of polio in children treated with the Salk vaccine was 0.016%, which was significantly lower than 0.057% in the control group. P is less than 0.001, and the sample size is more than 400,000. This leads us to conclude that the vaccine is effective in reducing the incidence of polio. All right, so again, we've got our descriptive statistics showing us the magnitude of the effect. We've got our p-value, our sample size, and we've got our interpretation or our conclusion. In this case, again, we rejected the null hypothesis and we conclude that the vaccine is effective. Now, again, I've left out the type of test, mostly because we haven't covered it yet. Okay, how do we interpret a non-significant result? So what if we get a relatively large p-value, a p-value that's greater than alpha? Do we conclude that the null hypothesis is true? Unfortunately, we can't. We never conclude that the null hypothesis is true, and that's because it's always possible that there is a small difference or a small effect, smaller than we were able to distinguish with our data. So for example, you can imagine we got some data on a vaccine that suggested that the p-value was quite large and we could not reject our null hypothesis. But it is possible that that vaccine works. It was just, it doesn't work effectively enough for us to detect it in our study. So we never accept the null. And so what would we say instead? Well, there's lots of different ways to word this, and I'm going to give you a few examples here. You could say something like, the data are compatible with the null hypothesis that blah, blah, blah. The data are consistent with the null hypothesis that whatever. We cannot reject the null hypothesis. We did not detect a difference between the control group and the treatment group. We did not detect an effect of the new vaccine. And so just remember that saying we did not detect is different from saying there is no difference, right? And so we can't conclude that there's no difference because that would be accepting the null. We have to say something like we did not detect a difference. Okay, so these are the steps to null hypothesis testing summarized on one slide. And you should be able to do this yourself. Given some data or some test statistics, you should be able to correctly report the conclusions. Okay, so I want to walk you through another example here. And so the research question here is whether the human sex ratio at birth is really 50-50 or half male, half female. And I want to note that the sex of a baby at birth is not the same thing as gender. Gender can develop differently from biological sex at birth, and gender as a phenotype is much more of a continuum. Okay, so suppose we want to test this question with data on babies born in Ottawa. I'm going to show you some hypothetical data and kind of build up this example. Okay, so our null hypothesis in this case is that there is a 50% probability of either sex at birth. And we're going to use an alpha threshold of 0.05, the convention in biology. So we're going to run some tests, and if our p-value is less than 0.05, we reject our null hypothesis, and otherwise we do not reject it. And so I'm going to use some fake data here, and let's say we have a sample size of 24 babies, and we record each baby's sex at birth. And so that's a categorical variable. Okay, so let's look at what we would do in two different data scenarios. Both of these are made up. I don't really have data on 24 babies. But in scenario number one, let's imagine our sample of 24 babies had 15 male and 9 female. And in scenario number two, let's imagine that our sample had 19 male and 5 female. Okay, so we've got our two data scenarios, and what I've plotted here is the null distribution. And so this is actually fairly easy to calculate by hand. So again, along the x-axis, we have every possible outcome we could get for a sample size of 24 babies, right? We could have anything between 0 males up to 24 males in that sample. And the y values for these data points are the probabilities of getting each of those possible outcomes. So the most probable outcome is if we had 12 males and 12 females in the sample. And as we get to more extreme distributions, like a sample with 0 males, that becomes very unlikely under the assumption that the null hypothesis is true. Okay, so let's take this null distribution and let's plot on the scenario of where we got 15 male babies and 9 females. So the blue line on the right represents the test statistic in that scenario, and then the second blue line on the left is like the equally extreme possibility. And what I'm going to do is I'm going to shade in the area under the probability distribution for any outcome that's equally or more extreme than the one we got. So if we add up the areas of those two curvy triangles, then we get our p-value, right? So it's the probability of getting an outcome at least as extreme as the one we got, assuming the null is true. And if you do that, the probability of getting of the scenario number one is a p-value of 0.31. Okay, so what do we conclude? Well, our p is greater than alpha. 0.31 is greater than 0.05. So we do not reject the null. And we'd say something like, we did not detect a significant departure from the null hypothesis of 50% male births. P equals 0.31, n equals 24. Okay, what about scenario number two? Here's the same null distribution, right? The sample size is the same, so the null distribution is the same. And we could plot on in blue the outcome we got, the test statistic we got, and then the one that's equally extreme. And it's really hard to see, but I've shaded in this kind of pinkish color again, the area under the curve for anything equally or more extreme than what we got. And we can add up those two areas and we get our p-value. And in this case, our p-value is 0.01 or 1% chance. And that is smaller than alpha. So in this case, we would reject the null and we'd say something like, our results indicate that there are significantly more males than females at birth. P-value 0.01, sample size 24. Okay, so this is a good point to pause the lecture and think about what questions you have about this so far. Write them down and bring them to Zoom on Thursday, and we'll discuss this whole null hypothesis testing procedure some more. And again, be patient with yourself. This is a hard thing to get. Students always ask, like, what's the best way to learn this? And the answer is lots of repetition, lots of practice. This question about the sex ratio at birth and whether it truly is 50% male, 50% female is one that people have been looking at for quite a long time. And this is some real historical data on the sex ratio of new babies born in London way back in the 1600s and 1700s, more than 300 years ago. And it's expressed here on the y-axis as a percentage. So we're looking at the percent of babies that were male in London, like for all births in London, what percent of them were male for each year between about 1620 to, 1720, 1710. So notice how every single year there's more than 50% male babies that were born in London. And these data were used by the mathematician John Arbuthnot, who was interested in this question of whether the sex ratio at birth really was 50-50. So he collected these data using church records of baptisms in London. And he was the first person to use probability to calculate to make an inference. And he calculated that if the sex ratio was 50-50, the probability of getting data like that was extremely small. It was like 1 in this huge, huge number. I don't even know what this number is. So it's 1 divided by that number is just infinitesimally small. And so this was before the discipline of statistics existed. It was before the word statistics existed. And he calculated the first null hypothesis test. And so we reject the null hypothesis, right, with this real data. The sex ratio at birth is not 50-50. Interestingly, although it was the first time someone used probability to test a scientific hypothesis, his interpretation chalked it up to divine intervention. He concluded that the excess of males must have been because of God. Here's some more recent data looking at the sex ratio at birth in countries of the world in the year 2012. And you'll notice that, so it's kind of indicated by color on this map. And you'll notice that the scale for these different colors, so these colors are ratios. And so a ratio of 1 means an equal number of boys and girls. And like the scale doesn't even start at 1. Every single country has an excess of males beyond the 50-50 sex ratio. So in every human population, the human sex ratio at birth is skewed toward more males. It's interesting to see that some countries have a greater skew towards males than others, and that may be because of kind of modern fertilization procedures and people being able to select the sex of the babies that they have. Now, as people age, the sex ratio evens out. There's different sex differences in mortality through life. And so this map is showing you data on the number of men per 100 women across all ages, across all these countries. And so the darker blue the country, the more women there are than men. And the kind of beigeier and darker beige the country, the more men there are than women. And so, generally, the kind of excess of males at birth evens out as people get older. And in some of these countries, there's an even there are an excess of males at older ages because of migration patterns and people moving into certain countries to work in a specific industry and perhaps send money to their families back home. If you're interested in this data, this link has some really interesting visualizations of these kinds of things. Bar graph shows you how the sex ratio varies by age. So by the time, if you're lucky enough to live to be 100 years old in your cohort, there are far more women than men at that time. Interestingly, the human sex ratio at birth may be influenced by major social events and even by disasters, natural disasters. And in Ontario, some doctors published a paper in a British medical journal documenting that in the months after Donald Trump was elected president, there were fewer boys born in Ontario than expected. And it's been something similar has been found in other cases where there's been kind of a big disaster or a big trauma that in the months after this big collective trauma, there are kind of fewer male babies born. And we don't completely understand the processes going on. I find it really perplexing that that like the United States election would be traumatic for so many people in Ontario, but could be real. And if you're interested in this, these are some other links where you can read about the biology of sex ratio at birth in other species. Okay, so in the last few slides here, I just want to pause and think critically here. What's so special about 0.05 for our alpha level? Like, is there something magical about 5? Well, the answer is no, right? Think about it. Is there really a big difference between an outcome with a p-value of 0.049 versus a p-value of 0.051? Well, with our null hypothesis testing approach, in those two scenarios, if we got a p-value of 0.049, we would reject the null. But if we got a p-value of 0.051, we would fail to reject it. So this is a problem with trying to agree upon a single threshold, right? A bright line where we're going to make a different decision on either side of that line. It can lead us into some kind of paradoxical situations. The biologist and mathematician Ronald Fisher was the person to first propose an alpha threshold of 0.05 because he thought a 1 in 20 chance was a sufficiently low probability to make a safe bet against a null hypothesis. But at the same time, he also argued that each study could set its own cutoff. And he never intended the alpha level of 0.05 to become this universal, dichotomous, hard cutoff the way it's often used or misused today. So there's no special reason for using 0.05 as our alpha level. And we should be really careful not to think dichotomously about statistical evidence. So the null hypothesis testing framework kind of forces us to make this dichotomous decision. But real evidence is not really dichotomous. And when we do this coin flipping experiment in class, it kind of gives you a sense of where your threshold of doubt is. And you can even calculate the probability value where you start to suspect that I'm not being honest. And it seems that most students have a threshold of about p of 0.1 or so. Anything less probable than that, they really doubt what's going on. But different people have different intuitions about where that threshold lies. And perhaps your intuition about the threshold depends on the research question. So why impose a single cutoff? Well, the idea is that if we all agree upon a value beforehand, then it makes things simpler for researchers and reviewers, and it means that people won't like choose the threshold that happens to be convenient for them at a time. And it's kind of like having a speed limit that we all agree upon. We know that 101 kilometers an hour is not much more dangerous than 100 or 99 kilometers an hour, but we need to agree on some kind of threshold, right? So just keep in mind that although we use this threshold approach when we do null hypothesis testing, that statistics should not be about dichotomous thinking, like yes or no, definitely true, definitely false. It shouldn't be about that. The whole point is that we have uncertainty and we want to quantify that uncertainty. And so even a super small p-value does not guarantee that our main hypothesis is correct. So just because you reject the null doesn't guarantee that you're correct, right? Like sometimes you get a small p-value just by chance. We'll cover that again later on in the course. And it's unfortunate that researchers are often misled by kind of overly focusing on the p-values and forgetting to do the kind of critical thinking. And we'll get into that more and more in future lectures. So just a couple more slides here. Keep in mind that the null hypothesis and the main hypothesis do not have equal footing in the process of inference. The null hypothesis is the only statement being tested with the data. And if the data are not consistent with the null, we reject it and we accept the research hypothesis or the main hypothesis. But if the data are consistent with the null, then we have to say we failed to reject it. And I actually really like this meme because this last point on the slide is hard to wrap your head around. It's like a weird thing to do. And so you just have to practice it a lot to get used to it and to avoid the kind of pitfalls. It's a really common pitfall to incorrectly accept the null. But we must never accept the null. We must fail to reject it. And so also keep in mind that rejecting the null tells us that there's likely to be some effect, and it tells us the most likely direction of the effect. In other words, is the vaccine better than the placebo? The opposite direction would be the vaccine might be worse than the placebo. But just because we've rejected the null, it doesn't tell us how big the effect is. How much better is the vaccine than the placebo? And so it's another common error to forget about reporting the descriptive statistics. The descriptive statistics are what tells us about the size or the magnitude of the effect. Okay, so that wraps up this introduction to null hypothesis testing. So again, write down your questions and I'll see you in Zoom on Thursday.